So hi, my name is Edith, and today I'm going to talk about two examples of how we design human computation systems so that it achieves what it's set out to do from the perspective of the requester, but also to satisfy the objective of the workers. Okay, so in the title, I just talk about human computation systems in general, but actually, I want to focus our attention on a particular problem setting, and this problem setting is attribute learning. So attributes are very useful because people organize data and make sense of the world using attributes. So what do I mean by attributes? So an example is this. So Louis Armstrong can be described by a set of properties. So these can be visual properties. It can be how he sounds like, or he can be described in terms of the kind of people that he is associated with. So he's a jazz musician, an African American. And it can be also relational. So that he has some relationship with some other objects in the world. So he plays saxophone and he won a Grammy Award and he sings Hello Dolly, for example. And since attributes are so important for information retrieval, we would like to learn attributes automatically. And so you see a lot of evidence of this in the research in many different communities like computer vision, music information retrieval, and text mining, and so on. So the basic message I want to convey here is that there's a lot of active research going on in learning attributes for different types of entities. So attribute learning is actually very hard for machines. And so this is where human computation comes in. The idea of human computation is that you have some tasks that are very difficult for machines to do. So for example, you have an image and you want to find out what's in the image. And even this is very challenging for current algorithms. And so you would like to give this input object to some system, which then coordinates a crowd to generate some kind of output for this task. And so our job is to actually design this system so that it's effectively taking advantage of the crowd. So these systems, human computation system, can be very straightforward, but recently there has been some work on adding some machine intelligence into human computation systems so that we can actually optimize the process of human computation. So for example, people worked on, in machine learning, they work on being able to ask more informative questions. So instead of asking people to annotate every single image, you only want to annotate ones that actually benefit your system. There's been some work on routing tasks to the best worker. So being able to observe a group of workers and who is the most reliable or accurate, and then routing tasks to the most appropriate person. There's been some work on real-time human computation. So being able to post a task and then get back the results almost instantaneously. And these are very important for applications like that help, for example, blind people recognize what's in front of them. People are only willing to wait for probably 2-3 seconds before they give up on the application. And there's also been some work on selecting the best workflow. What I mean is maybe you have multiple tasks and they're all slightly different, so how do you actually sequence them in such a way to give you the best outcome? And most of this work is actually done on, I would say, micro-task paid crowdsourcing platform like Mechanical Turk. But what my work is focused on is actually something quite different. And these are systems where people don't get paid. And they perform the task because there's something actually intrinsically motivating for them. So an example is games with a purpose, where you have for example, the ESP game is one of the first games, first example of games with a purpose, where you give an image to two people, and they would independently generate some kind of tag. So maybe they say drawing and map and so on. And then at some point, they find a tag that matches. And then that becomes a reliable label for that image. And so this game has been very successful in that it draws in, it drew in millions of users and has lots of images annotated, and Google got interested in it and bought it. And so all this data that's collected from game players are then used to drive image search. And so great, so we have these very powerful games, and we want to, we can get lots of work done very quickly. But it turns out that the design of these systems is actually very tricky. So on the one hand, you have requesters that have some kind of requirements, like they want useful data, determined by that particular person. Maybe it's volume, or maybe it's specificity of the data. But on the other hand, you have a crowd of people, and these are game players, who really don't care much about what you're doing. All they care about is having fun, being rewarded with points, feeling like they're on top of the world. So this talk is about how we actually design a system that can satisfy both objectives, because if you don't, then essentially such a human computation system wouldn't work. And in particular, I would describe our approach, which is to first design for the humans. What I mean is the workers, and then incorporate some kind of machine intelligence to overcome the limitations of the human workers and to complement their abilities. So before I go into, I'm going to give you two examples of this type of design. But before we go into that, I'd like to describe a framework for attribute learning that will let us talk about attribute learning, games with a purpose, and also the joint human and machine computation within the same language. And so let me just define what I mean by attributes. So I define attribute as a function that maps some kind of entity to some real values between 0 and 1. So for example, an entity can be an image, and the attribute function can be, does the image contain a dog or something? And 0, 1 will represent the probability that that attribute actually applied to that image. And so there's two other terms that are very related and commonly used. For example, in machine learning, we talk about classes and labels. And I also see them as attributes. For example, is a dog can be a class for a computer vision problem. And when people say tagging, what I mean is really a tuple where you have the attribute, the entity itself, and the value for that, which is usually 1. And so in this framework for attribute learning, what we're trying to do is actually learn a matrix, a huge matrix, where the entities are the rows of the matrix. So these can be images, music, video, and text. And the columns are, you can think of as all the attributes in the world. And the cell of the matrix is the value of the attribute for a particular attribute and for a particular entity. And so there's actually two problems within attribute learning. One is, if you're given an entity, you want to find the columns that actually are relevant to the entity. So for example, if the entities are images, then an attribute like loud might not actually be relevant. And the other problem is attribute scoring. So we would like to find the value for an attribute for a particular entity. And so you can think about games as a particular query model for you to access this matrix and edit it. So in an ESP game, for example, you have you give two players the same image, and one player might say dog, and the other person say cat, and they may agree on a tag called kitten. So in this query model, basically you're giving out an image, but then you're getting back one row of the matrix with the most relevant columns filled in. So this is an interesting model in that it is different from the typical machine learning or active learning model where you give a particular entity and you receive a particular label back. And so within this framework, you can also think about humans and machines taking role in both discovery and scoring. So you can have somebody pinpoint what column is actually relevant. You can also have a text mining algorithm that goes out on the web and scrape the web for a set of images and see what kind of tags are relevant. And you can also have humans generate values if you give them some kind of human processable representation. For example, if you give them an image. For machines, you have to do a little bit more, so you have to give them something that the machine can process. For example, for an image, you can give them a color histogram or a SIF feature and so on. So is there any questions so far about the way I'm describing attribute learning and the framework? I guess this is kind of hidden in the query model itself. So yeah, I don't think this actually capture how people generate, like how you use reward to influence how people generate the role of the matrix. So I just assume that I hand something out and I get something back. And that's it.
So you can imagine that the ESP game generates a certain distribution over the possible properties. And if you just ask the people to put out the label, you're going to generate different distributions.
Right. So using different types of games, you're probably going to get different types of.
Can you repeat the question? I couldn't hear.
Yes, sir. So I was asking how the game rules actually going to affect the properties being generated by human contributors.
If you just flip the usual game around and say, generate words that nobody else has generated about this, you're going to get a very different set of attributes.
Right. Yeah. Okay. So I'm going to give two examples of systems I've worked on where we had to look at both how to satisfy the human-centric objective and the task-centric objective. So the first is music tagging. So attributes are used a lot in music information retrieval because it's, I guess, the simplest way people can think of how to query for some piece of music they're looking for and how to discover them. So you can imagine it would be great if we can just put into search engine this type of query and get back something that's completely relevant to us, like giving a folk song that's soothing, playful, and not too cheesy. Could be really useful for a date, but probably if you put something in like that today, it won't work. And so how do we collect these attributes? So one idea is that we can use the ESP game mechanism. So the ESP game is really a game template. Where you give the same entity to two people, they generate some kind of output, and if the output match, then you trust that output as being reliable. And in fact, it has been reused many, many times. So I can probably name 10 to 20 games that use the same kind of game mechanism for different types of things, for images, for music, for knowledge extraction, and so on. And so the ESP game, I think, was very successful because people were able to generate useful data. They were able to do it quickly, and they were doing it quickly while having fun. And so when I first came to CMU, I was asked to look at how we collect attribute for music. So, well, since the ESP game is so successful, we should just apply it. Because it will just work, and then we'll just sell it to Google again and make lots of money. So this is what we did. We had a game that followed the ESP game mechanism. We give a single piece of music to 2 different people, and we ask them to generate some kind of tags. And then we will reward them when they match on a tag. And that completely failed because people had a very hard time coming up with tags that match each other. So about 36% of the time, players actually skip around because they were typing in things and they would never match. Or they end up entering something very generic like music just to score in the game, but the word music is useless to us. So you essentially violated all 3 of these things that made the ESP game effective. So it wasn't producing anything useful. It wasn't producing anything useful quickly because people kept skipping, and they weren't having fun either because they couldn't score in the game. So the idea of the new Tagatune is that we created a new mechanism that does not rely on agreement. So this is how it works. You give 2 people either the same piece of music or 2 different pieces of music, and you ask them to enter tags. And these tags are shared between the 2 players, so they can see what each other is typing. And at the end of the game, they asked to guess whether the 2 pieces of music are the same or different. And so just to illustrate how it works, maybe we'll play 1 round of the game. So on this side, you typically would enter some kind of tags. And then on this side, on the right side, you actually see what's coming from your partner. And then at the end, both of you would choose whether you have the same piece of music or not. So how many people think it's the same? Okay, so you're right. And then you'll be rewarded with some points, and you'll be very happy. So the results were pretty dramatic. So before, we had 36% of the times people skip. Now only 0.5% of the time people skipped around. So it was a significant improvement. Over 7 months, we had 14,000 unique players. Some people are, they just come and play once and they leave. And other people stay for a long time, so they play 420 hours worth of games in 7 months. And we collected a lot of data. And the usage has, for human computation game, it always has a lot of usage at the beginning, and then it levels off. So it has been like 3 years now, and there's still people coming to play every day, so that's very encouraging. So why is this mechanism effective? So in the ESP game case, we had people independently generate output, and we rely on them to find basically a column of the matrix where both people would think is relevant. But for music, there's so many ways to describe music, and the language is not always standardized. So this becomes very difficult. So in the input agreement mechanism, which is what we call the Tagatune mechanism, we remove that. So we allow open communication between the partners. And so it doesn't require them to agree. And the other interesting property, I guess, is that instead of giving players a single object and asking them to annotate it, you give them a set of objects, and you ask for something that distinguishes between the set of objects. So what ends up happening is that we get attributes that are very specific and discriminative, as opposed to an ESP game, which traditionally have the problem of gathering very common tags. Like if you give people an image of a car, they would say car instead of Honda Civic or something like that. So this is great. Now, by doing this, making the game more human-friendly, we actually created other problems. So I mentioned that Tagatune actually collects tags that are very discriminative and specific. So here are some examples of the tags we get back. So we have some very imaginative tags that are very specific and actually, very interesting, like Cookie Monster vocal. I can see that being a good description of Louis Armstrong's voice, for example. But these are associated with very few examples. We have tags where people would just talk to each other, so they would type same or different in order to indicate to the other person what they're choosing. We had problems in the beginning where people actually enter the email address to each other, which was a huge problem because we then take their email address and we use them in a session where there's only one player. So these email addresses basically got broadcasted to a lot of people. But in any case, these are like what we call communication tags. So like when they talk to each other, saying, hi, how are you, where are you from? So we get things like that too. We get a lot of spelling mistakes. And a synonym is also a big problem. So you basically have tags that really mean the same thing, but people just talk about them differently. So how does it affect our task-centric objectives? So if you think about, we want to do attribute learning, we want to actually basically fill in this big matrix. And with Tagatune, we can actually fill in this matrix partially, pretty well. But we would like to have some kind of automated method to actually fill in the rest of the matrix. Now, if we give this to a standard machine learning solution or algorithm, this is kind of a big problem because we have a lot of relevant columns. So these can be between 10,000 to 100,000 tags that are unique. And then many of them are actually identical. So for example, mellow and soothing really mean the same thing, and the examples that they share, that they have in each class should be combined, but they're not. So you end up having a lot of columns with very few examples, and some columns having lots of examples. So it's very unbalanced. In music information retrieval, for example, a standard way is just to do binary classification for each tag that you can have. So for the tag soothing or classical and so on, they will train a binary classifier to learn whether a piece of music actually has that attribute. And so these methods are no longer useful because it's not data efficient in that you have to throw away a lot of classes or a lot of tags that have only a few examples, because you just can't learn from that. And it's not very time efficient because you basically have to train a separate classifier for each tag. And so our approach is to actually have a more compact representation for music, and then use it somehow to generate the tags. And the representation that we pick is a topic model. So what is the topic model, and how do we represent music with it? So we see music, each piece of music as a document basically containing the tags that we collected from Tagatune. So here's actually a particular topic model that we learn using the Tagatune data. So you see in this topic model, there's 10 topics, and they're all about slightly different things. So topic 10 is about female vocal opera singing. And topic 3 is about Middle Eastern type of sounds. And then topic 7 and 8 are about wood instrument and new age type of sounds. And so for a particular piece of music, it's basically represented as a topic distribution. So an opera music, an aria or something will be represented by topic 4 and 10. And another example is some kind of new age song that sounds kind of weird, and the topics that dominate are 7 and 8. And so we choose this representation because we have an hypothesis about how people actually generate, how players in Tagatune actually generate the tags. So the idea is that you have a piece of music you give to a game player, and they have in their head some kind of topic distribution in their head about that piece of music. And they also know what's in that topic. So what they do is they pick a topic out of this topic distribution, and then they go into this topic and then pick a tag based on tag distribution, and then they generate a tag. So what we observed are the tags that we get back from Tagatune, and also the music, which we can represent using audio features. What we do not know and what we're trying to learn is what is the topic model that actually explains the tags that we get back from Tagatune, and for each music clip, what is the topic distribution? So that's essentially our learning problem. And so our algorithm actually have a two-step process. In the first step, we try to take all the tags that we have from Tagatune and learn a topic model over it. And this is a very standard, we use a very standard technique called latent digital allocation, which is a graphical model that explains the generative story that I just told you. And after we do this phase 1 of training, what we get back is essentially a topic model that explains the tags. And then what we want to do is assign each piece of music a topic distribution, and then learn a mapping from audio feature to these topic distributions. And then at inference time, when we have a new piece of music, what we can do is infer the topic distribution for that piece of music and then use that to generate tags. And so we compare three different methods. Our approach, which maps audio features to topic distributions and then use that to generate tags. Binary classification, which maps audio features to each tag. And random tagging, which basically where we just randomly pick a topic and then randomly pick a tag out of that topic. And so very short summary is that we find that our approach is comparable to binary classification in terms of annotation and retrieval performance, but it's much stronger in terms of data efficiency and time efficiency. So when we learn the topic model, we actually don't throw any tags away. We just put the whole thing through the system. It's also, the training is also much faster because we just have to train a mapping between audio feature and about 10 topics, as opposed to 10,000 tags. And so in summary, we found that output agreement mechanism that the ESP game implements is not very good for music. And so in order to satisfy the workers, which in this case are game players, we invented a new mechanism that is actually poses an easier task for people and give them higher chances of success. And in doing that, we actually created a problem where we have fast and noisy open vocabulary that was generated by the Tagatune mechanism, and we had to create a new learning algorithm to actually leverage that kind of data.
You could imagine taking, a synonym dictionary and collapsing the tags at least that much before you.
Yeah, there's a lot of pre-processing or post-processing that we never did. So
you're effectively learning that dictionary.
Right.
Which is more robust, but I kind of wonder how well you do over that naive approach of just fix some synonym dictionary up front and then use that and then use the tag classes that you get from that.
Right. Yeah, so that's definitely, we haven't actually done anything with the data before we actually try this new learning methods out. But yeah, we could get potentially, if we do a lot of post-processing on the data, which we typically do before we release the data set anyways. So the tag-tuned data has actually been processed and turned into a data set, but then we end up having very few classes at the end because it would just be, collapsed.
So at first it made perfect sense to me why your explanation for why the original ESP game wasn't working well with music, that there's diversity of tags, and it's harder to identify a small number of labels that people would easily agree on. But it seems that it's not just properties of the domain, but also I don't know, the player's abilities and goals that make one method versus the other work. So, for example, I was wondering what happens if you try to apply this method to tagging images.
Mm-hmm.
If the player's goals are just to win, then we could probably agree by just saying, okay, color in the upper left corner is blue, and you see that it's red in yours, and we know it's different, and not generate any. We could win the game without generating any useful tags. So, I guess my question is, do you have any kind of general sense and something that might even approach, maybe something that might even approach some kind of model for what the player's abilities and goals might be that could help predict in a new setting whether one or the other of these mechanisms, or both, or neither, would work well?
So the player's goals in some sense are influenced by how we design the game, because we ask them, right? So in the ESP game, we ask them to agree. And in terms of like what
is their goal just to
I think
there's also this sort of having fun, like maybe players wouldn't want to just win by agreeing on the color in the upper leftmost pixel of the image.
Well, they definitely want to. I think from my experience, they definitely want to feel like they have accomplished a task successfully. So I don't know if it means, like, to some people it means points. So like a lot of people really want to stay in the top 10 players. So they're the one that actually play for hours and hours. But then I think other people it's just frustrating not being able to finish even a particular round of the game. So even in the user studies that I did, I see people, they're basically cheating because they just want to be able to complete the task. So I think maybe fun, the idea of fun is actually very analogous to being able to accomplish the task successfully.
How do players play this game? Is it that player A writes, the song is soft, and then player B thinks, like, is my song soft, and then agrees and writes soft as well? Or?
Yeah, they might write soft, or they might write some other word that indicates soft, but not exactly.
They take whatever the other person writes as a trigger compared to what they hear and then react on that. Right.
So one thing I didn't point out, but it was in that slide with loss of tags, is that we get these negative tags too. So one person, if one person says soft and the other person music is loud, they would say not soft. So I end up getting a lot of negative examples, which the ESP game would never collect, I think. So yeah, it is reactive, the tagging. Or
so curious as to if you tried anything to resolve the open vocabulary problem that was within the original mechanism. For example, like you might think that once you've identified a couple of tags, maybe offering a couple other attributes that you could just click on to use, or if there was an autocomplete that would just make it easier to type something that already would agree.
Yeah, I haven't tried that, but that could be a good idea. Yeah. There's some reservation to restricting people on what to do.
Encouraging them to do more.
Right. Usually, like, we find that if we give a free text box, it's much better than limiting them, for example, by number of characters they can type in, or even the type of things they can type in, which is done a lot in games. So in Verbosity, for example, it's a game where they give you templates because they know that people are just putting it very noisy information. So they try to put in template, like, it's... So Verbosity is a game where you have to guess a word. So you have a secret word called apple, and the other person has to type in some clues for the other person to guess apple. So they will have these templates, like it is red, or it has something. But that totally doesn't work because people are... It just encourage them to cheat more because they feel restricted.
Mm-hmm. And I'm wondering if success or failure in solving the tasks is correlated with length of participation. And if so, if as a game designer, maybe, I don't know, I suppose maybe you can lie to people and say, okay, if you see that they fail 10 times in a row and they're about to give up, tell them, okay, you succeeded on this tag. Go on to the next
right.
What is correlated with length of participation, and how can you increase it as a game designer? I suppose that's my general question.
We haven't really looked at whether if they play longer that they were more successful.
I suppose the question is the opposite. If they're successful, do they play longer?
Oh, if they're successful, do they play longer? Yeah, we haven't really looked at that question, but yeah, you can imagine. Yeah, so we can actually do a lot in that space because to find two players that actually come simultaneously and have them play with each other is actually very hard because people come at different times. And so a lot of times players come, they're actually playing with the bot. And there's a lot we can do with the bot because we basically control who the partner is. So there's a lot, yeah, we can lie. Yes.
You're talking about? No, sorry. Do you want me to say it again? So did you actually run your trained topic model in the generative direction to generate descriptive terms?
Yes.
Okay. So I was just wondering, in that, what's the connection with the audio features that you talked about from the song? Did that influence the alpha parameter or some part in that?
So we learned the topic distribution, and then using a topic model, we can assign to each piece of music a topic distribution. So we have a set of training data. And so so we find we find a mapping between the audio features and these topic distributions. So when a new piece of music come in, we say, what kind of topic distribution does this piece of music have? And it might say, topic 7 and 8, and then using that, we generate the tags. So it's not always clear that the tags generated would correspond to what's in the music. And so there's actually more sophisticated learning methods that take into account classification when they build the topic model. So those might be actually a bit better.
Can I just ask a clarification question about which set of the data that you used for the learning algorithm? So did you use everything collected from the game, or did you use those data that the players actually correctly answer whether they're listening to the
I used everything. Yeah.
Used everything.
Yeah, even all the things with spelling mistakes and so on. So one thing the topic model does very well is picking out these topics that mean nothing. So these words like you or me or I or how are you or something, those get grouped somehow into a topic.
Do you think the performance of the learning algorithm will be improved if you restrict yourself to the data that players actually bring?
Yeah, I'm not really sure because I think the data is just as noisy, probably. So, could we answer questions at the end, perhaps? Yeah. So I can go on to the next example. So the next example I want to go into is image classification with birds. So there I was actually interested in a different challenge in this attribute learning framework, where we have some kind of entity, but then the attribute is actually something that people are not very familiar with. So a particular category of bird, for example. Does anybody know whether that's a finch or not? Not really. And art, for example, whether it's what kind of style it is, it requires some kind of special knowledge. So this is actually a problem of how do we actually have people score attributes when they don't actually know what, how the properties of the thing they're looking at map to an attribute. And so you can think of many ways of scoring an attribute. So one idea is that you can give a single entity to somebody and ask a binary question. So is Vienna a capital city, for example? Another way is that you can give them a single entity but ask a multiple choice question. Is Vienna a capital city, country, or continent? But then there's a third type, which is you can give them a whole bunch of entities and ask them a binary choice question. Like, which of these is the capital city, Vienna, Budapest, or Seattle? And so in this work, we focus on this type of query. And so you can think of this type of query as a grid. So you have an attribute like capital city, and you have a bunch of entities you're interested in, knowing whether that attribute actually apply to those entities. And so how would we have people score these attributes? So one idea is use the ESP game mechanism. The problem with using that mechanism is that there's a very simple way for people to cheat. If we reward them based on how much they agree, they can just select everything and basically win every time. So how do we prevent people from selecting everything blindly? So the idea of the complementary agreement mechanism is that we ask the two players to do different things. In fact, the opposite things. So we ask the first player, which I call the positive worker, to select the entities that have an attribute. And then I ask the other player, which I call the negative worker, to actually select the ones that don't have the attribute. And then we score them based on some measure of how many things they selected in total and penalize them for any overlap that they have. So what I'm essentially doing is asking the two players to generate some kind of output to constrain what each other is going to enter. So I see some confused faces here. Do we have any questions about this?
I was just wondering why they don't also cheat by, if you're a positive worker, you say yes on everything, negative worker, you say no on everything.
So it's just kind of in the scoring rule, I guess. So if we require them to type in at least one thing, or if we ask them if we score them based on like how many things they actually selected, and then penalize them for the amount of overlap between the two players.
So both players have to select the same
right.
thing.
And so we use bird classification, image classification as a case study. And we actually have 28 different birds family that we looked at. And we actually implemented a game called the perfect split based on this mechanism. So, and there are different types of modes of this game. So in the scoring mode, the players basically get an attribute like a blue head. And the positive player would have to select the images that have blue head. And then the negative player would have to select images that don't have blue head. Now, in this scoring mode, we actually give the players the attribute. In the discovery mode, we can actually ask one of the players to generate the attribute. So instead of giving them an attribute like blue head, we ask the positive player to enter an attribute to split the images. So they can choose any attribute that they like blue head or long tail or whatever. And then that attribute gets propagated to both players, and then they go ahead and select things that have the attribute and do not have the attribute. There's a third mode, which I call the targeted discovery mode, where the positive player actually gets a set of images, but some of them are highlighted already for them. So what they have to do is actually enter an attribute to distinguish the ones that are highlighted from the ones that are not highlighted. And then the negative player would get to select images that don't have the attribute while the positive player waits. So are those three modes of the game clear? Yeah.
So in the second mode, why is there any score on the value of the attribute you choose? For example, in the previous case, somebody just said cat, in which case it's very easy to win, right? One person says that none of these is a cat. Do you see what I'm saying? Like, is there any score on like how useful an attribute is when the user inputs it?
No. Yeah, so in your case, in the example that you gave, if persons say cat, they still have to select, I still ask them to at least select one image in the game.
Okay, so there's a constraint that at least one of them has to be...
Right, we ask them they have to select at least some things. Each of the player have to select at least something. They can't just say none of this image.
But with this, you can imagine having a preference for something which splits the number of images evenly, right? Like,
right. Yeah. So I have tried different types of scoring mechanisms. Some of them, and I tried the one where I asked them to split things evenly, and that's actually quite tricky because people were taking a long time because the system doesn't know whether it actually splits evenly. So the players were really agonizing over how to choose an attribute that actually split them. So we ended up having a simpler scoring mechanism that just says you have to select at least one thing, and if you select all the images that are in the grid and that you didn't overlap, you'll get the maximum number of points.
Couldn't players cheat by saying select all the images in the top row? That would always
yeah, so we randomized the images for the two players.
Okay.
Yeah, but we did see that even in our user study that they type row 3, column 4, and actually sometimes it worked, and sometimes it gave them something, and other times it didn't give them anything. So because we really only have 8 images, so even if you randomize it, you might have some chances of clicking on the right thing. So we have, so we looked at 4 different versions of the game. In one version, the game only gives the scoring mode, and the game actually provides a category name like Finch as the attribute. There's the discovery mode where one player got to choose how to split the images. There's the targeted discovery mode where one player gets to describe some highlighted images. And the last mode, it provides an attribute, but it's an attribute that's from previous games. And so the last 3 versions actually is a more open-ended type of entry where the players get to choose what attributes and how to annotate those attributes. Whereas in the first case, it's equivalent to a categorization task where people are given a category and they're asked to do that directly. And so we recruited 30 people from a service provided by Carnegie Mellon for recruiting users. And we put people into pairs to play the game, each version of the game for 12 minutes. And they had to fill in a short questionnaire at the end. And we randomized the order of the versions that they get so that we have less carryover effects from one version to the other. So I think I might be missing a slide here. So the goal here actually, let me go back to. The goal here is that I'm actually trying to find out what is the difference between asking people to directly categorize a bird image versus giving them some kind of freedom in choosing how to annotate the attributes and then using some kind of machine learning algorithm to infer the categories. So this is where I'm trying to compare the first version versus using the data collected from the last 3 versions and combining that with machines. So in terms of the human-centric objective, so how much did the players enjoy the game or could play the game? Here I'm showing the round score that the players get. First one, the yellow bar, is actually the version where they're given a category as the attribute, and they have to say, is this bird a finch or is this bird a owl? And the last 3 versions are the discovery and targeted discovery and the scoring mode where they're given an attribute, but the attribute is not a category. And up arrow is up is better. So you can see that the players get higher score in the last 3 versions. They also selected more things in total. So between pairs of players, they actually selected more of the images in the grid. And they also overlapped a lot less. And this is kind of consistent with the questionnaire results. So we asked them 3 questions: how much they enjoyed the version of the game they just played, how confident they were about the answers, and how difficult did they find the game. And in all 3 cases, there's a statistically significant difference between having people just openly generate attributes and versus asking them to actually annotate the category directly. So the other thing we're interested in is actually how accurately people are able to categorize the birds. So we have ground truth data, so we're able to measure for each type of categories how precise or how accurate people were in categorizing the bird images. And you can see that some of the more unfamiliar species, people are doing very poorly on. So the question is whether we can improve this precision where humans actually fail. And so the idea is that we have these columns that correspond to attributes that people are not very familiar with. And instead of asking people to score them directly, we collect some kind of other types of attributes that they choose, so colorful or odd white spot on head. And then we use those attributes to actually infer the attributes that we actually want to learn about. And so this is the slide I thought I was missing, but it came later. So the idea is to compare human categorization, which correspond to the first version I told you about. First is a hybrid categorization approach where you you allow people to just enter things as they wish, and then you take the data and actually learn a classifier to predict the attributes we're interested in. So the results turn out really nice. So remember the yellow bars are the human categorization results, and you can see that I ordered them so that the higher ones are in front. And you can see that for the more unfamiliar attributes or category, people are doing poorly on. And the hybrid categorization approach actually improved over the ones that people have trouble with. So what this means is combining humans and machine actually, in this case, help with the task that we are actually interested in. And at the same time, we are not restricting people to a task that they don't enjoy. What's that? Sorry. So we can also look at the kind of features that the classifier picked up on. So for chickadee, for example, chickadee is a bird that I think most people recognize by sound other than by pictures. So if I ask somebody to say, what is this bird? I think it's unlikely that somebody could recognize that as chickadee. But the machine learning classifier actually was able to pick up on some of the attributes that people have entered and use that to infer chickadee much better than humans can. And so in conclusion, in this case, we have a task that we want people to do, but they're not very familiar with the attributes. So instead of forcing them to do that, we actually just allow them to freely enter other types of attributes. And then we tackle the real task, which is to do bird classification, but we do that by leveraging some kind of human intelligence in the loop. So if we have one take-home message, is that our approach is really to try to achieve the human-centric objective in human computation games, but at the same time balance that with the task-centric objective of the system. And we show two examples of this in music tagging, where we invented a new mechanism that is better than the ES-speaking mechanism for players. And we invented some new learning algorithm to take advantage of this noisy crowdsourced data that we collected from the game. In the case of bird classification, we have a task that's very difficult for game players, and we turn that, we basically allow them to enter attributes that they choose themselves, and then use machine learning algorithm to perform the actual task we're interested in. Just one slide about future work. So far I've talked about a very manual way of thinking about how to design these systems to balance the two objectives. But a lot of these games, for example, have different modes, like in the perfect split, they have different modes that have different costs and benefits. So some modes might be harder for players, but then they'll have more information for the task you're interested in. So some kind of decision theoretic method for automatically choosing not only what images to present, but also what type of query to ask through different modes would be interesting. So we just started thinking about human computation games as query models in machine learning. So started talking to a few people about this, but it would be interesting to have some kind of theoretic model for thinking about new types of queries that's different from the current active learning model. And this work actually has quite a bit of application in citizen science. So I did bird classification partly because there's been some work at Cornell interested in this topic. What they're trying to build is this tool called Merlin, where a birder will go into the field and they see some birds that they want to identify, and they will go back to the computer, and the computer will ask them 20 questions, like, is this red? Does it have a blue head? And so on. And at the end, give them some kind of candidate images. And what they're stuck on is that they don't have these attributes. You know, they have some attributes in some database, and it's not really processed. It's not in the language that normal people talk about birds with. So they're also trying to put human computation games up on their website and to collect attributes for birds. Another example is a different project where they're trying to figure out the attributes of different species, like under fossils, for example. But a lot of these attributes are not very easily explainable to people. So for example, in this case, I have a skull of some animal, and I want to know if the post-orbital bar is incomplete. And so, so this type of task that requires some training, how do we actually turn that into a task that people can do or would enjoy doing? So this is the end of the talk, and we welcome any questions.
Okay, well, so I'm still interested in, I guess, Salil's question from earlier. So if I want to think of people as just maximizing their points or trying to get through the task for some reason, they get utility just from points. So I'm wondering, do you have an intuition for how much of the success of these mechanisms comes from the incentives, like points, and how much just comes from like innate human honesty, where people just want to be helpful?
People are not innately honest. Yeah.
Good incentives are really required here.
Yeah, I don't know how much the magnitude of the points actually matters. We haven't really tested, you know, if you give them 1,000 points versus 10 points. Yeah, but if you have a system where you don't, like you allow a lot of stuff, like, you know, you give them a lot of freedom, they would try to maximize points and not care about the data. Because at the end of the day, they really want to just have fun and waste time. So.
But if you could just get it by clicking a button, people wouldn't keep doing that for hours.
They might. No, if you have also a scoreboard where you say who is the fastest clicker.
A lot of ways to incentivize people.
Right.
So in your graph, you showed that you know, adding the machine into the mix improved the one that the humans were doing for that. But there were a lot that towards the other end of the graph where it did worse. I'm just curious why that might be. Like, you know, the
Yeah.
gull.
Yeah, I mean, the machine learning algorithm might not work as well if the attributes that people provided are not discriminative against other classes.
Yeah.
So we haven't looked into detail why certain ones don't work and other ones do, but.
Well, it means like for hawk, for example, it
Mm-hmm.
means that a person's not putting in the word hawk as an attribute. Like, if you ask someone to say which ones are hawks and which ones
Yes.
aren't, they can
Mm-hmm.
do that. But if there's a hawk on the screen, they're not going to type in the attribute hawk and say that's a hawk.
So in some of the cases where people are really familiar with the animal, they would actually put in hawk
I mean,
or owl
it
and
would be the
duck.
opposite, right? That easily recognized. Like I know what a duck or an owl, right? So
Mm.
that's what I would type.
Right, yeah. So we do see that people type.
So Todd's suggestion, I think, is if you put up some large bird of prey and ask me if it's a hawk, I'll probably say yes. And maybe that's why the score is high on the yellow. But if you put up a bird of prey and ask me what it, I have to come up with a word. I don't know if I put a hawk or a falcon or, you know, I don't know, tell a bird. Birds of prey.
Yeah. We also tried, so these are family names. We also tried going one level down, so asking what type of hawks or what type of owl. And we just haven't done enough experimentation to get enough data because it's too sparse. So we really should have, or what we should do next, I guess, is to pick certain, like 3 or 4 categories and go deeper and say, you know, then how much would the machine help? And my guess is it will help a lot more because people will be much more unfamiliar with those. And I also actually tried this with birders. So I call up some people at Cornell and I make them play the game. And they they score perfectly with the first version of the game where you just ask them for the category directly. So that's interesting, actually, an interesting idea of mixing expert and non-expert, where the expert can give you the labels and the expert can give you the attributes.
So in the human experiments, you would have shown images with hawks and non-hawks, right? And that's how you got those results. But like when you were learning the indirect attributes, where the user specified what the attributes were they also on sets where you had hawks and non-hawks? Because then it's possible that users would select attributes which let them discriminate between something which is in one category or the other. Like if the attributes you're learning to figure out if it's a hawk or not are from sets,
we definitely we have two different versions when we pick from those two randomly. One is we pick from two or three categories, and the other we pick from 5 to 8 categories. But we find that if we don't have some initial idea of the groupings, it's very hard for someone to look at 8 different bird images and come up with something that's common between them. So we rely on like our initial ground truth set to actually pick the images. So we pick at least some that belong, to one of 3 categories, and then we present those to players.
Right, but I was just talking about this particular comparison of this particular graph, right? Instead of comparing with, if you showed people an image and said, choose which are the hawks, and otherwise, and the second version is show the same set of images and said, choose your own tags, right?
Yeah.
Would they, in that comparison, would they actually select?
Would they say hawk?
No, would they select attributes which help them over?
Yeah, so this is actually what I tried in the targeted. So this whole idea of the targeted discovery mode, where I highlight some images and I say, give me some attribute that distinguish this set from the other. What I was trying to do is like, well, if I have, give them hawks, I selected all the hawks and the rest are not hawks. Would they give me attributes that actually distinguish them? And it's inconclusive at this point because actually there's a lot of variation within the single family. So sometimes, maybe hawks is not a good example, but some other family, they all look different. So people actually had a very hard time coming up with an attribute that is common between the highlighted ones that are not, that you can't see in the other. So maybe it has to do with also maybe minimizing showing people fewer images might actually be easier for them.
Also, the improvements that you made with the music tags, did you try doing that with images again? Because I wonder how much you would improve on or not.
Yeah.
The original music.
Yeah. We haven't tried that, but I can see it generating more specific tags for sure, but more noisy ones too.